Okay, so this part of section 1.3 is it's quite weird. The significant digits, especially when we get towards like actually using significant digits. Just to be honest with you, when I learned this in school, I learned this in a science class, not the math class, and didn't make sense to me then why they do what they do. Still not sure it makes sense to me now, but we're gonna go with it. I'll explain the rules, and we'll just work with the rules, and that's how we'll go about this. So significant digits are digits in measurements that carry meaning about the precision of the measurement. So apparently that's why. All right, so here are some of the rules when it comes to identifying significant digits. All non-zero digits are significant. So if it's not a zero, it counts as part of the significant digits. And you can see those examples. Rule number 2, zeros between two other significant digits are significant. So the zeros between two non-zero numbers are all considered significant. And you can really see that here in that second example on this one, that, the 4 and the 8, as stated by Rule 1, are significant. Rule 2 says all the zeros in between them also count as significant. So that's why that one in total has 7 there. Okay. Third rule, zeros at the end of a number to the right of a decimal point are significant. So these zeros matter if it's behind the decimal place, if it's to the right of the decimal place, but only to the right of the decimal place. Zeros to the left of the first non-zero digit in a decimal are not significant. That one's confusing, okay? Zeros to the left of the first non-zero digit in a decimal are not significant. So in this example here, the 3 is that first significant non-zero number. All these other zeros are basically meaningless, because they're to the left, not to the right. Only the ones to the right, if there were zeros behind it, would be significant, but not the ones to the left. The ones to the left are not significant. I don't know why. I really don't. That's just the way they write these rules. So yeah, and then zeros at the end of a number without a decimal place or decimal point are assumed to be not significant. So here you can see your significant digits, and then the ones to the right, but without a decimal, are non-significant. So to the right with a decimal, significant. To the right without a decimal, not significant. Strange stuff, really. But yeah, those are the rules. So it does get very confusing, but here's a really good way of figuring out how many significant digits there are. And it's by filling in this table. So this table, you're going to look for the non-zero digits. So anything 1 through 9. Anything that's not a zero, you're going to count it. Then we're going to look at the zeros between those numbers and count them. And then we're going to look at the zeros that are to the right of a decimal. And it's specifically the end zeros, because as we mentioned, these zeros here are technically to the right of the decimal, but they're not at the end of the number. They're in front of it, so they don't count if they're in front. So the word end zeros is very important there. So when we look at this number here, try to zoom in a little more, we're gonna fill out this chart to count out the significant digits. So non-zero numbers, there's the 6, the 4, and the 5. So there's 3 non-digit numbers. So that counts in our little total here. Then we're looking at zeros between two significant numbers. So we see those zeros between that one, we're counting it, and we'll see the zeros between the 4 and the 5, and we're counting it. So there are 4 of those numbers, 4 of those zeros that lie between other numbers. And those all count. And then we're looking at zeros that end zeros to the right of the decimal. So there is a 0 here that's at the end on the right side of the decimal, so that 0 does technically count as well. So all in all, there are 3 plus 4 plus 1, 8 significant digits in this problem. I don't like the fact that they chose these examples, but I'll show you examples that are different than these. But we'll look at these for now. So example B, the non-zero digits. Let me write it out so I can have it like bigger circle. 710.080. So non-significant digits, we have 7, 1, and 8. Or I'm sorry, I don't know what I said, non-zero digits. 7, 1, and 8. So there are 3 of those numbers. Zeros between 2 significant digits. So there are some zeros that lie, no. There are some zeros that lie between the 1 and the 8. There's a 0 here and a 0 here. So there's 2 of them that lie in the middle between them. So we're going to count those 2. And then we're looking at end zeros to the right of the decimal. So there is a 0 at the end to the right of the decimal. So we're going to count that one as well. So there's 1 there. So that gives us a total of 6 significant digits, which means all of them are significant in this case. But yeah, let's look at some other ones that are a little different. We're going to do the your turn ones. We're going to count the significant digits there, and we're going to follow the same rules. Okay, first let's look at number 5. A student claimed that 0.045 and 0.0045 have the same number of significant digits. Do you agree or disagree? I'll let you think about it real quick. If you want to pause, I'll actually scroll back up. If you want to see these rules or these rules, and then try to determine whether those have the same significant digits or not. And the answer here is agree. That yes, they do have the same number of significant digits, because they have this one has 2 with the 4 and the 5, and these zeros don't count, just like I believe it was the 4th rule up here. Zeros to the left of the first non-digit 0 in a decimal are not significant. So all those zeros here didn't count. So that's the exact same thing that's happening here. Those zeros don't count. And the second number is exactly the same. It's got the 4, 5 at the end, but it has all these zeros in front of it. Those zeros don't count. So 2 digits here, 2 digits here. They both have 2 significant digits. All right, so let's look at number 6. So if we follow the rules, right? Non-zero digits. Let's count those first. There's a 5 and a 2. So there are 2 non-zero numbers. Now let's look for zeros between the 2 significant digits. There are no zeros between the 5 and the 2. So there are no significant numbers in that regard. And then end zeros to the right of the decimal. There are no zeros at the end to the right of the decimal. So if I'm filling out those 3 categories, this one, and this one, I have 2, 0, and 0. So in total, that means there is only 2 significant digits in that number. Now, number 7 is a really interesting one. So remember, follow these same rules, okay? First, the non-zero digits. There's only one number that's non-zero. Okay, it's that 1. Now let's look at the second one. Zeros between 2 significant digits. Well, there's 1, but there's no other number, right? If this ended with the 1 here, then I would count all the zeros in between it. But there's only that one number, so there is no in-between section. So there are no zeros between 2 significant numbers, because there's only that one significant number, that one right there. There's no second one that I can look in between with. So there's none for that second category. And then end zeros to the right of the decimal. Now these zeros are end zeros, but the decimal would be here. And these zeros are not to the right of that decimal. Those zeros are on the left of that decimal. So these zeros do not count at all. Because remember, even though they're on the end, they are not to the right of the decimal being here. So it doesn't count. So there's only one significant digit in that entire number. It's just 1. Okay. Now 8 is fascinating as well. For 8 to really work, you kind of have to actually do the second and the third steps in the opposite order. So it's kind of confusing. Non-zero numbers, there's 1. We have that. Now, this one, because we have end zeros to the right of the decimal, right? End zeros to the right of the decimal, right? All these zeros, that zero that I'm pointing to counts. So all the numbers between the 1 and that 0 will also count. So this makes 5 significant digits. 1, 2, 3, 4, 5. All of them are significant digits. If you just had the number 10 and just said 10 feet, it would only have one significant digit because there's no decimal place. If you make 10.0 though, because you've introduced this decimal place and because you have the 0 to the right of the decimal place, that would mean all those numbers are significant, so you'd have 3. So that's why here we have 10.000. You've got these zeros that do count because they're on the right side of the decimal. So therefore, all those digits will count in between. So that's all 5 of them would count. It's very, very strange. I know it's very, very strange. I can't really explain why the rules are that way, but they just are that way. So let's try to read this. Maybe it'll help us a little bit better, or maybe it'll just confuse us even more. We'll see. When performing calculations with measurements of different precision, the number of significant digits in the solution may differ from the number of significant digits in the original measurements. Use the rules from the following table to determine how many significant digits to include in the result of a calculation. This is the part that really doesn't make sense. But here we go. Operation, addition or subtraction. The rule, the sum or difference must be rounded to the same place value as the last significant digit of the least precise measurement. So you would think that they would want the most precise measurement, but they don't. They want the least precise measurement. For multiplication or division, the product or quotient must have no more significant digits than the least precise measurement. So we're going to look at the one that's least precise. However many significant digits that has should be the same number of significant digits our final answer has. Again, this seems very counterproductive because you're kind of ruining your accuracy and you're ruining your precision as well. But that's the art of significant digits. They're really insignificant digits, but here we are. Okay, so let's look at this example. It's already worked out. We'll try to make sense of it. Find the perimeter and area of the given object. Make sure your answers have the correct number of significant digits. So, a rectangular swimming pool measures 22.3 feet by 75 feet. So, first and foremost, keep in mind that 75 is less precise. Remember, we're looking for the least precise one. 75 is the least precise because it doesn't go into that decimal. If you're wondering where that's coming from, watch part 1. If you haven't watched part 1, I explain how you can tell which numbers are least precise or more precise. But anyway, 75 is the least precise number here. Just keep that in mind. Find the perimeter of the swimming pool using the correct number of significant digits. So remember, perimeter is adding up all 4 sides of the pool. So you'd add up, let me use red. you'd add up this length, this length, this length, and this length. This side plus this side plus this side plus this side. You would have up your perimeter. So if we have a pool that measures 22.3 by 75, then this is 22.3, 75, and this side would also be 22.3, and then the other side would be 75. So there's your pool. So the perimeter is adding up all the lengths. So you add up 22.3 plus 75 plus the other 22.3 plus the other 75, because a rectangular has 4 sides. The least precise measurement is 75. We mentioned that already. And that 75 has 2 significant digits. The last significant digit is in the ones place. So round the sum to the ones place. The perimeter. So our answer is 194.6. That's what we really have as an answer. But because we're using significant digits, right, this tells us to round to the same place value as the least significant digit, or the least precise measurement. So the 75, its last significant digit, as it mentions, is in the ones place. So that means our answer should be rounded to the ones place. So 194.6 rounded to the ones place is 195, because the 0.6 would round the 4 up. It's very nonsensical. I would agree with you on that. If we want to find the area of a pool, so remember, area is length times width. So this is kind of like a part A of the problem. It's like a part B of the problem. So this part is a whole new question. Find area, you do length times width. So we know the length is 75, the width is 22.3. So we would just multiply those together, and we have the area of the pool. But because we're making this area based on the number of significant digits, we are going to have no more significant digits than the least precise measurement. So the least precise measurement is 75, which again has 2 significant digits. So our answer should only have 2 significant digits. Now, this answer that we have, 1,672.5, has 5 significant digits, but we have to round it to the nearest number that has only 2 significant digits. So 1672.5, 16 would round up all the way to 1700. Because you have the 72.5 here, all of this would round up. We have to stop at 2 significant digits, so we can only use up to these 2. So that's why we're looking at all of this and rounding it all the way up. 72.5 would round up instead of down, given the fact that it's higher than 50. The 72 at least, right? 72 is higher than 50. So we're rounding up to 1700. It's very strange. Doesn't make a whole lot of sense, but that's what significant digits do. All right, let's look at this question. A rectangular garden plot measures 21 feet by 25.2 feet. Find the perimeter of the garden using the correct number of significant digits. So remember, perimeter is adding up all 4 sides. So we have 21 feet on these sides, and we'll have 25.2 feet on these sides. So we add up all 4 of these numbers. So we'd have 21 plus 25.2 plus 21 plus 25.2. And we get 92.4. Now that's our answer, but we can't leave that answer because we have to use the correct number of significant digits. So the least precise measurement is the 21 feet, because this, 25.2 goes to the tenths place, which is more precise than the one that only goes to the ones place. So the last significant digit is in the tens place, meaning we have to round the 92.4 to the tens place. So since the 0.4 is not big enough to round up, we actually round this down to keep it at 92 feet. Or the ones place. Did I say tens place? I meant ones. I don't know what I said. But the 21 feet, it's last significant digit is in the ones place. We're rounding it to the ones place. 92.4, rounding it to that whole number 92. To find the area, we do length times width. So we have the 21 times the 25.2. We just multiply that and we get 529.2. Oops. But again, because we're rounding this to our significant digits, our least precise measurement has 2 significant digits. So then our answer should only have 2 significant digits. So we have to round it to these places. So that means taking the rest of these and rounding it up or down. So 9.2 would round up. So our final answer would be 530 because the 9.2 is going to round this 2 up to 3. So 530. So the least precise measurement is 21, which has 2 significant digits, as we mentioned. So round to a number with 2 significant digits, and we've done that. The answer is 530. Okay. Number 9, in the example, why did the area of the garden and the swimming pool each have 2 significant digits? The answer to this is because the least precise number in both those examples only had 2 significant digits. When we were looking at the garden's least precise number was 21, and 21 had two significant digits, which is why we rounded our final answer to 2 significant digits. And the same is true with the swimming pool. The swimming pool least precise number 75 has 2 significant digits, so our area also had 2 significant digits. So it's all based on basically this rule right here, the multiplication or division rule. That's why. Is it possible for the perimeter of a rectangle garden to have more significant digits than its length or width does? The answer would be, that's a good question. Yes, actually. For example, if the width was 13 feet and the length was 501 feet, the perimeter would be 1,028 feet, and 1,028 has 4 significant digits. So yes, that is possible. That is possible. Okay, now if you want to try these, you're welcome to. I'm going to go ahead and throw the answers up here. So again, you can pause the screen, give it a try, work it out, and I'll throw it up here. So for perimeter and then area. Perimeter, we take the 7.6, add it with 8.25, and then add the other 7.6 and add the other 8.25. So our actual perimeter comes out to be 31.7, but our number that's least precise is 7.6, and that has 2 significant digits. So this number also should have 2 significant digits. 31.7 means rounding 2 significant digits means we're rounding this. So we're going to take the rest of this and round it up or down. Since it's 7, we're going to round up. So our answer will be 32 feet. Oh, I did that. I keep mixing up these rules. Hold on, I apologize. I did the area rules again. So adding, subtracting, we're supposed to take the lowest significant digit value place. Okay, so yeah, 7.6 is the least precise, but 0.6 is the place we need to round to because adding, subtracting. So 31.7 is actually already in that place, so we don't really have to change it at all because it matches the least precise number, if that makes sense. Area, I was doing the area rules. Apologize again. Like I said, this is crazy, right? 7.6 times 8.25. We multiply them together, we get 62.7. So now now I'm gonna get these rules right. So for multiplication or division, you look at how many significant digits there are, and your answer should have that many significant digits. So not with perimeter. With perimeter, when you add or subtract, you're supposed to look at your least significant or your least precise measurement and then round to that same decimal place. So the least precise measurement was the 0.6 here, 7.6, which is the 10th place, which means our answer should be rounded to the 10th place. Whereas for area, our least significant value or least precise value has 2 significant digits, so our answer should have 2 significant digits, which means we round that up to make this 63 square feet. It's very crazy. It's very crazy. So for perimeter on number 12 and area on number 12, perimeter, we would take 91 plus 91 again, plus 203.2 plus 203.2. So if we add them all up, the actual perimeter is 588.4. Okay, now the least precise number is 91. And so 91 is rounded to the ones place, which means the answer here should be rounded to the ones place. So that means taking the next number and rounding it up or down. So 0.4 would actually round it down. So 588 will be our answer. For area, we do length times width, 91 times 203.2. And our area is 18,491.2. 18,491.2. Now again, our least precise number is 91, and that has 2 significant digits, so our answer should have 2 significant digits, which means we should stop here and then round the rest of this. So 491.2, all of this, because the 4 is there, will round down, so our answer will just round to just 18,000. Very imprecise, but it's the way the world works with significant digits. Okay, if we do this, I'll make another video, but I'm going to stop the video here because it's already kind of running long. So again, apologize for the fact that this makes no sense, but that is what significant digits do. It's certainly interesting. So I will see you guys in the next one. Bye.